Welcome to Brand Media. Thanks for joining us. The world is full of complex systems. They are all around us. The weather, the stock market, and even our own bodies are examples. For a long time, scientists thought we could predict these systems perfectly. If we just had enough information, we could know exactly what would happen. But then came chaos theory. Chaos theory tells us something both exciting and unsettling. It says tiny changes can have huge effects. It challenges our intuition about cause and effect. Imagine a drop of water falling into a still pond. We can easily predict the initial ripples, but what happens next is much harder to predict. The ripples interact with each other. They bounce off the edges of the pond. Soon the pattern becomes extremely complex. This is chaos in action. Even with something simple, like a drop in a pond, the future quickly becomes uncertain. Chaos theory isn't about randomness. It's about systems that are deterministic but unpredictable. In a deterministic system, the same starting conditions always lead to the same outcome. Think of a pendulum swinging back and forth. Its movement is determined by its length and the force of gravity, but chaotic systems are highly sensitive to their starting conditions. A tiny change at the beginning can lead to dramatically different results later on. This sensitivity to initial conditions is a key part of chaos theory. It means even the smallest error in our measurements can make long-term predictions impossible. It's like trying to predict the exact position of a leaf floating down a rushing river. Every tiny gust of wind and ripple in the water will have an effect. The most famous illustration of chaos theory is the butterfly effect. This thought experiment asks a simple question. Can a butterfly flapping its wings in Brazil cause a tornado in Texas? The answer, according to chaos theory, is maybe. It seems impossible, but it highlights the interconnected nature of our world. Let's imagine that butterfly. Its wings create tiny changes in the air pressure around it. These changes, though minuscule, can interact with other weather patterns. Over time, through a complex chain reaction, they could potentially influence the formation of a tornado thousands of miles away. The butterfly effect isn't about a direct, linear relationship between the flap of a butterfly's wings and a tornado. It's about how small events in complex systems can have far-reaching and unpredictable consequences. It's a powerful reminder that we can't always predict the impact of our actions, no matter how small they seem. Of course, not every butterfly flap leads to a tornado. The weather is influenced by countless factors, from ocean currents to solar radiation. But the butterfly effect reminds us that even small changes can have a ripple effect. It tells us that complex systems like the weather are inherently unpredictable in the long term. Chaos theory might seem like it's all about randomness and unpredictability, but there's a surprising element of order within the chaos. This order reveals itself in patterns called strange attractors. Imagine a pendulum again, but this time imagine it's being influenced by magnets placed around it. The pendulum's movement will no longer be a simple back-and-forth swing. Instead, it will trace out a complex, looping pattern in space. This pattern is its strange attractor. Strange attractors are like maps of a chaotic system's long-term behavior. They show us the range of possibilities within the chaos. A fascinating aspect of strange attractors is their fractal nature. Fractals are geometric shapes that are self-similar. This means they look the same at different scales. A classic example is a snowflake. If you zoom in on a snowflake, you'll see that each tiny branch resembles the whole snowflake itself. The strange attractors of chaotic systems often have this fractal quality. They are infinitely detailed, with complex patterns repeating at smaller and smaller scales. This connection between chaos and fractals is a beautiful example of how order can emerge from seemingly random systems. Chaos theory isn't just a theoretical concept. It has real-world implications in many fields. In meteorology, it helps us understand the limits of weather forecasting. While we can make reasonably accurate short-term predictions, long-term forecasts are much more challenging due to the chaotic nature of the atmosphere. Small errors in our measurements can quickly amplify over time, leading to very different outcomes. In finance, chaos theory helps explain the unpredictable nature of the stock market. The prices of stocks are influenced by a myriad of factors, from economic indicators to investor sentiment. These factors interact in complex and often unpredictable ways, making it difficult to predict market crashes or booms with certainty. Ecosystems are another example of chaotic systems. The populations of predators and prey are constantly in flux. influenced by factors such as food availability, disease, and competition. Chaos theory helps ecologists understand the resilience of ecosystems and how they respond to disturbances. Even our own bodies are subject to the laws of chaos. The beating of our hearts, the firing of our neurons, and the regulation of our hormones are all examples of complex, dynamic systems. Chaos theory is helping medical researchers understand the complexities of human health and disease.